Hi, everybody, and welcome back. It's section 9.1, complex numbers. It's real actually privilege to be the person to introduce these things to you if you have not seen them before. So this is an expansion of our concept of number, and it turns out to be remarkably useful. And so a lot of things are the same, going to be what you're used to, and a few things are a little bit different. So we're going to go through this, I think, a little bit quickly. I'll try to go through the arithmetic quickly because it's quite straightforward, and I'll try to make sure that we're communicating well. So I, of course, have my usual vocabulary thing here at the top. So we've got this idea of a complex number. And what do we mean by that? We mean a number that has two parts. It consists of two pieces, and we usually write it like this: x plus iy. And x and y are real numbers, and I is the square root of -1, or I squared is -1. So let's just write an example over here. For example, 3 plus 2i is a complex number. The real part of it is 3, and the imaginary part is 2. And together, that number is called a complex number. It has a real part and an imaginary part. Okay, we can take a conjugate, and the conjugate means, if, for example, here, if I have this one here, 3 plus 2i, the conjugate is this guy here, 3 minus 2i. Okay, so it is the same two numbers here, but the sign here is changed. That's the complex conjugate. And then we use this little symbol here, this C with the bar, to mean the set of all complex numbers. I mean, this is exactly, we've been using this symbol all along to mean the set of all real numbers. So we have the set of all complex numbers. The modulus, the word modulus. Modulus of a complex number is its length, if you will, or we usually say absolute value. So if we have a complex number like we have over here on the side, let me just write it again, z equals 3 plus 2i, then we can calculate the modulus of z by taking the square root of 3 squared plus 2 squared. Okay, so that's what we call the modulus. The Argon diagram is a two-dimensional representation of the complex numbers. We're going to come to that. We put the real part on the x-axis and the imaginary part on the y-axis. And you'll be happy to know that there's we can represent our complex numbers in a rectangular form and in polar form. So you're going to draw on your knowledge of polar coordinates from Math 151 or 152, and we're going to add to that a little bit. Okay, so let's take a look at a little bit about where the motivation for these things comes from. We're talking about roots of polynomials. Roots of polynomials are a highly actually studied property, and there's actually lots of things. Polynomials are very nice functions for a variety of reasons, and they also are very interesting in their own right. So let's just talk about the polynomial, and then we have a question. Does every polynomial have a root? And that means if we have some given polynomial, is there some input to it that gives us 0? So we have some polynomial like this, p of x equals x cubed plus 2x squared minus 42. And we wonder, is there a number, p, and this number here is r, so that if I put r in there as r cubed plus 2r squared minus 42, the result will be 0. And if there is that, if I'm guaranteed that that number r exists, can I find it? Like, how would I find that? So let's just take a look at the roots of polynomials and see where that leads us. So here's a polynomial, x squared minus 1. So we're asking, what are the roots? What values of x make this thing equal to 0? So that is clearly going to be when x squared is equal to 1, and that will be when x is equal to plus or minus 1. So, I mean, this is telling me that f of 1 equals 1 squared minus 1, and that's 0. So 1 is a root, and f of minus 1 is minus 1 squared minus 1. That's also 0. So I've got two roots, and I found two zeros. That is not a coincidence. That number is 2. This is a quadratic. Okay, let's now look, though, at another example. Looks extremely similar, right? Here we have f of x is x squared minus 1. Now we're going to look at a different function, different polynomial. F of x equals x squared plus 1. And we're going to say to ourselves, is there a number that we can plug in here that makes this thing equal to 0? And so we do exactly the same thing. We think, okay, is there a number x where I square it and add 1, I get 0? Well, that would mean that x squared would have to be equal to minus 1, or x would have to be equal to plus or minus the square root of minus 1. That would work. Now we don't maybe know what this actually means, but if we're willing to just accept that, we'll notice that, of course, if we square it, we get 1 and we get -1, and then -1 plus 1 is 0. So we get the zeros. Now you'll notice I put the plus or minus here in the front right here. Okay, I just want to remind you that this symbol like that, if I write it like that, for example, square root of 4, that the answer there is 2 and 2 only. The answer is not -2. Okay, this little symbol right here means a positive root. Okay, and it's a function. The square root is a function. So we have it this way. Square root function looks like that. With this part is eliminated, right? We're just looking at the positive portion. So it means the positive root. That's why the plus or minus is sitting there. So when you're trying to solve the quadratic equation, for example, where you're using the quadratic equation, for example, you have a polynomial ax squared plus bx plus c equals 0, and you want to know what are the zeros, you are used to being able to go x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and you are used to putting that plus or minus there. Okay? You put the plus or minus there because from this guy, you only get the positive root out. So you have to incorporate that plus or minus. Okay, just want to be clear about that. So this number right here, this guy, the guy who provides a 0 to this polynomial right here, x squared plus 1, that we define that number to be I. I is defined to be the square root of -1, and it is such that I squared is -1. So I'm just going to write that again, just because this is a key point. I is defined to be the square root of -1, and if I square both sides, I see that I squared is -1. Okay. Otherwise, if you just say, well, okay, this is a bit weird, a number like I haven't seen before, and where is it? And like, is it on the number line, or I'm not totally sure. We may not be totally sure how to conceptualize it. That's fine, but let's right now just accept we got a new number, and the number is defined in this way. Now, once we do that, like it just behaves exactly like the numbers you know and love. It doesn't behave differently. So it is just a regular number in the terms that it's associative, distributive, commutative. You can add and subtract. So all those sort of things you can do with regular numbers: add, subtract, multiply, divide, take exponents. What else? I mean, they could be solutions to equations. We just saw that. Solutions to equations. What else? You could have complex valued functions. You could take derivatives and integrals of those. So what we're doing is not really, we're not introducing something that is completely unusual in a sense. What we're doing is we're saying, here is a new number. It behaves like the numbers that you're used to. Okay, it's clearly though not a real number. It is not on the number line anywhere. It has a property that's this property that when you square it, it's -1, and that is not a real number. Okay. All right. So here's the definition: expressions of the form a plus bi or a plus ib. It doesn't matter which order. This order doesn't matter. Okay, so that's a and b are real, and then we put them together like that. It's a complex number. The I is in there. Okay, we got the set of complex numbers. We already talked about that. If we have a number that looks like this with only an imaginary component, we call that a purely imaginary number or an imaginary number. The real part, so these symbols here just extract the real and imaginary parts. Let me just give an example of that. In fact, I have here already an example coming. So here, the real part of 1 minus 3i is 1. Okay, that's the real part, and the imaginary part of 1 minus 3i is -3. Okay, so we could just we have this function that just takes a complex number and either extracts the real part or extracts the imaginary part. Okay, let me just do a couple more examples. The real part of 7i, well, 7i is a purely imaginary number, so the real part is 0, and the imaginary part of 7i is 7. Similarly, the real part of 2, unsurprisingly, this is a number you know and love already, that is 2. And then the imaginary part of 2 is 0. It doesn't have an imaginary part. Okay, so we can, when we're working with these things, we could decide, oh, we want to know what the real part of this thing is, and then this is the manner we extract. Okay, we're going to go through addition and multiplication via examples. It's not difficult. What you do is, if you're going to add, for that matter, add or subtract two complex numbers, what you do is you just do the real and imaginary parts separately. Okay, so I got to go 2 plus 1, I get 3, and then I'm going to go minus 1 plus 2, and I'm going to get 1. So this answer here is 3 plus I. So what I'm doing is adding and subtracting the real and imaginary parts independently. Add, subtract, real and imaginary parts separately. That's the procedure. So you basically, in some sense, if you're gonna add and subtract complex numbers, you got to do twice the amount of work. Okay, distribution works the same way. So here I've got 2 plus 3i multiplied by I. I simply multiply the I in onto both parts. So this becomes 2i plus 3i squared. As soon as you see an I squared, that is minus 1. So then that becomes 2i minus 3. And often, you don't have to do this necessarily, but we often write the real part first. So we would sometimes write this like this there. Okay. Multiplying, it's just a distribution thing, just like you would do any other way. You'll 1 times 2, 1 times 3i, so that's 2 plus 3i, and then you say minus I times 2, and minus I times 3i, that is minus 3i squared. Then you combine, so that's the 2. I'm going to combine these two and get I, and then this is minus 3i squared, but I squared is minus 1. So that becomes minus 3 times minus 1, that is plus 3. Then I can put those things together and I get 5 plus I. You don't have to write it out in quite this much gory detail when you do it. After you've done 50 or 100 of them, you can usually, the I squared just sort of goes to minus 1 in your head while you're doing the arithmetic, and you can do it more succinctly. Okay, same thing here. If we're subtracting, we're basically effectively distributing the minus 1 and adding, if you want to look at it that way. So this becomes 2 minus 1 plus 3i plus I, and it becomes 1 plus 4i. That's a subtraction. And then here's a multiplication of 3 things. You can see there's one that's just a real number, and then there's 2 complex numbers. You can do it in any order that you wish. These things commute. So let me just, I'll just do the 2 afterwards, but now I'm going to multiply the 2 numbers, the two complex numbers together, these 2 guys right here. So I'm going to distribute in the same way. I'm going to go here minus 1 times 2, that's minus 2, minus 1 times 2i, that's minus 2i, and then minus 3i times 2, minus 6i, minus 3i times positive 2i, that becomes minus 6i squared. And I'm going to put some of these things together. We'll just start right here. So I got minus 2 there, and then I see minus 8i, and then I'm looking at that and I say, oh, there's that I squared, which is minus 1. Minus 1 times minus 6 is 6. I put that there, and I keep going. 2 times 4 minus 8i, and then I can multiply that as 8 minus 16i. Okay. Practice, just practice with a few. You can enter them into Wolfram Alpha and check your answers, or I'm sure the textbook no doubt has a bunch of arithmetic calculations, particularly practice problems A, where the answers are in the back. Just do a bunch of practice until you can do the arithmetic. Okay. One important consequence of the imaginary numbers is that every polynomial, this is a major theorem, every polynomial can be factored into linear factors if you allow the complex numbers. Okay, so this is the fundamental, that's always a major clue that it's important. This is the fundamental theorem of algebra. Okay. A 3-degree polynomial has 3 linear factors. A 4th-degree polynomial has 4 linear factors. A 17th-degree polynomial has 17 linear factors. You may recall from Calculus 2 when you did partial fractions that we factored polynomials into linear factors and irreducible quadratics. So that's what we always did, because you can always do that. Now what we're saying is, of course, if we have the irreducible quadratic, we can't actually factor that, but we need to introduce the complex numbers. And once we do that, then we can factor any polynomial down into the degree of the polynomial number of linear factors, okay, over the complex numbers. So that is what we're doing. Major theorem. Okay, so additional arithmetic. The conjugate, I already said what this is. If we have a number here like that, the conjugate is defined as, we change the sign on the imaginary part, and you'll notice the bar over the z. That's how we indicate that is the conjugate of z, the z with the bar over the top. The modulus, or we sometimes call that the absolute value. Okay, that is the defined in this manner. It is the square root of a squared plus b squared. We're going to geometrically see what this what this looks like coming shortly, but you should recognize this right now as looking very similar to the norm of a vector. Okay, let's just do a few calculations. We've got 2 complex numbers here, z and w. Let's just write out first. Let's just do these 2 guys first. We want, what is the conjugate of z? So I take a look there at z, and I change the sign on the imaginary part, and so the conjugate of z is 2 plus 3i. And similarly, the conjugate of w, I change the sign on the imaginary part, it's -4 minus 3i. Okay, now I'm going to calculate the modulus, or the absolute value of those 2 complex numbers. This is basically the distance from the origin, the same way what absolute value means on the real number line. We're going to geometrically see this coming soon. Okay, so let's just calculate it, given our method of calculating. The modulus of z is the modulus of 2 minus 3i, because that is z, and that is the square root of 2 squared plus minus 3 squared, and that is 4 plus 9, which is 13 there. So that is the square root of 13. Let's calculate the modulus of w. The modulus of w is the modulus of -4 plus 3i, and that is going to be the square root of -4 squared plus 3 squared plus 3 squared, and that is 16 plus 9. That's 25. I take the square root, I get 5. So each complex number has a modulus. Okay, now we're saying, given the general form of a complex number, a plus bi, a and b are real numbers, show that z times the conjugate of z is the modulus of z squared. So all we're going to do is calculate the left side, calculate the right side, and show that they're equal. Why don't you do that yourself? Stop the video, calculate z bar, z times z's conjugate, calculate the modulus of z squared, and go, hey, they're the same. And then you've showed this to be true. Okay, I will now do that, but better to do it yourself than watch me. Okay, so z is a plus bi. That means the conjugate of z is a minus bi. And then if I calculate z times z conjugate, that looks like this, a plus bi, a minus bi. And I then distribute and multiply this whole thing out. So I get a squared, and then I get minus abi, and then I get plus bai and minus b squared I squared. Okay, these guys cancel out, and I get a squared plus b squared. So normally you're used to factoring the difference of 2 squares, right? That has been something you've undoubtedly done for quite some time. What I'm now saying is that you can factor the sum of 2 squares. Okay, so we've calculated that. Now let's calculate on the other side the modulus of z squared. Well, that would be the modulus of a plus bi squared, and the modulus of a plus bi is the square root of a squared plus b squared, and then we're squaring that, and so that is a squared plus b squared. Okay, they're the same. That's fine. There you go. All right, we've talked about addition, subtraction, and we've talked about multiplication. Now we're going to talk about the multiplicative inverse. As you know, I've been hashing on about this in a variety of applications. So this is the number that you multiply another number by in order to get the multiplicative identity element, which is still 1. Okay, so we're going to look at the multiplicative inverse, and we denote that in the same way we've denoted an inverse all of the time. Now, in this case, it is also the reciprocal, just like it is for real numbers. But it is defined to be the complex number such that when I multiply the inverse of Z with Z, we get the multiplicative identity element. Okay, you contrast that with matrices. A times a to the minus 1 is I. Multiply a matrix times its inverse, and you get the identity element, which is not just a number. It is the, if we're in the 2 by 2 case, it is the identity matrix. Okay, this is the same idea. So what we want to do is figure out how are we going to calculate the multiplicative inverse of a complex number that is not 0. So we've got some complex number, Z equals A plus BI, and we want to know what number do we multiply that by in order to get 1. And we can see that the reciprocal will do this because that is going to be equal to 1. Okay, so the inverse of a complex number is in fact the reciprocal, just like the inverse of 2 is 1/2. Okay, so let's figure out, we've got here then Z to the minus 1 is going to be 1 over A plus BI. Now comes a key skill. We're going to be using this all the time. And I want you to think of this in the same way that you learned in high school about how to rationalize a fraction. It's the same idea. We're going to multiply top and bottom by the conjugate. There's the conjugate. So we're multiplying by 1. We're not changing anything, but we're multiplying top and bottom of this fraction by the conjugate. And we get A minus BI in the numerator. And we get in the bottom, well, we just did this multiplication right here, didn't we? So we found out that that was A squared plus B squared. So then we can separate that into 2 pieces, A squared plus B squared minus I times B over A squared plus B squared. There. That is the inverse. I do not suggest memorizing this. Whenever you want to find the multiplicative inverse of a complex number, you can simply just go through the procedure with the actual numbers. And we're going to do some examples coming up. Okay, the other way of thinking of this is to see that, it's not erasing for me. Okay, there we go. To see that the inverse, I can see this by looking now, is actually the conjugate. That is this thing right here. The conjugate divided by the norm, the absolute value, the modulus squared. Yeah. Again, I don't suggest memorizing either of these forms. We do have that. Okay, so here let's just do a calculation the way I would do it if somebody just gave me a random complex number and said, could you please calculate the multiplicative inverse? I would say, okay, and I would not use either of these formulaic ways of doing it, but I would just simply go ahead and do it for the one I'm being asked for. So let's do Z equals 1 plus root 2I. We're going to do that, and we want to know what the inverse is. So then I would say, okay, fine, that is equal to 1 over 1 plus root 2I. I'm going to multiply by the conjugate on both top and bottom, just like I did in the general example above. Again, feel free to stop the video, do it yourself. You can do all these calculations yourself, and then start the video and go, okay, I did it right, or I did it right and Brenda made a mistake, or other way around. And then you can check with Wolfram Alpha, and then that's better than just watching. Okay, so I go ahead and do this, and I see what's on the bottom is the modulus squared. So maybe I'll just make that calculation above here like this. 1 plus root 2I, 1 minus root 2I. And then I make that calculation here just so it's out of the way. And I see that that is 1 plus 2, that is 3. Okay, so I'm then going to continue. I know that the denominator is 3, and I know what the numerator is, 1 minus root 2I. So this is 1 minus root 2i over 3, and that means 1/3 minus root 2 over 3i. We tend to keep them separated like this too. We tend to write it like this rather than writing it like this. So you can clearly see the real and imaginary components. Okay, I'm going to leave the other one for you to do. I'll just put down what I did. I calculated the inverse of W, and I got this number here. You calculate it. It's the same. I've just done 2 examples in general and 1 specific. So calculate it out like that. Okay. Let us then take a look at what W over Z will look like. W over Z means W times Z to the -1, and we just calculated this. So we can do this as a multiplication. That'll be W, that's W, times the inverse of multiplicative inverse of Z, like that. And I can make this calculation and distribute it just again. I've done several of these examples, so I'm just going to write down the answer. Please stop the video, check my arithmetic. But I made this calculation and I got this thing here, root 3 plus root 2 over 6 plus 1 minus square root of 6 over 6 times I. Okay. There you go. We can now add, subtract, multiply, and divide. Let's take a look now about how we're going to visualize and conceptualize these things. So we can represent a complex number. We can think of this in some ways as a 2-dimensional number. We can even think of them somewhat like vectors in R2. We have to be careful about generalizing everything, but we have in some ways now, we've actually seen this 3 times, and we're going to just provide the context about what's different and what's the same, but it's the same. There are a number of similarities. So we have this idea. We have a point, which we sometimes say P, and we say the point AB. And we mean some point in the plane. We can say we have a vector, B. And that vector, I could say it has components A and B. And particularly with the textbook that we're using, we have often been writing the vectors like that. Okay, either way, either notation is fine. I could also now say I've got a complex number. I've got a number, Z, and it is A plus BI. Somewhat, I mean, these things are somewhat all the same. There's 2 degrees of freedom. There's 2 things that we're picking, 2 real numbers, A and B. In all 3 cases, we're picking 2 real numbers, A and B. Okay, and when we think of it as a point, let's just do that. When we're thinking of it as a point, AB, we come along here, 1, 2, 1, 2, 3, and we come here, and this is 2, and this is 3, and we're like, hey, there's the point, 2, 3. Okay, when we're thinking of it as the vector, let's see, we're thinking of the vector 2, 3. We tend to draw it in this manner. We come along here 2, and we come up here 1, 2, 3, like that. And we identify that, and we tend to draw the line from the origin to the point and put that little on there. That is actually a straight line. Use your imagination on that. That is a straight line. And so we have the terminal point of the vector at the point 2, 3. And then now what I'm saying is we can also be thinking of 2, 3 in this manner. Z equals 2 plus 3i. And we would come along here. Now what we're going to do in this case is we're going to relabel the axes. We're going to call this the real axis, and we're going to call this the imaginary axis. We're going to come 2 units along the real axis, and we're going to go 3 units on the imaginary axis. And we're going to come to that point right there. And we're going to label that as 2 plus 3i. Okay. One thing to point out right now is, let's just go down here, 1, 2, here, minus 3. You will notice that this point right here is 2 minus 3i, and that is, in fact, the conjugate of Z. So we have taking the conjugate is a reflection across the real axis. Okay, so some things that are common and some things that are different. Adding and subtracting complex numbers is exactly the same as adding and subtracting the vectors. Multiplying a complex number by a real number corresponds identically to multiplying a vector by a scalar. here's an important point. Multiplying two complex numbers does not correspond to either the dot product or the cross product, which we barely are using, right? So it does not, multiplying two complex numbers is not the same as taking the dot product. Okay, the modulus of a complex number is corresponding to the norm of the vector with the same components. Okay, and we already sussed this one out, that we have a reflection. Okay, the conjugate is a reflection over the real axis. Okay, now on the next page here, we have a whole lot of properties of the conjugate, modulus, and multiplicative inverse. So they're listed here. I don't think it's of value for me to read them. You can read. And so, I mean, let me just read the first one, and that's it. Like, so this would be the conjugate of W plus Z is equal to the conjugate of W plus the conjugate of Z. Okay, so these are properties of complex numbers. So what I'm going to tell you to do, suggest strongly, not tell me, suggest strongly. Take two numbers, like let me just randomly kind of pick one, like there. Take Z equals 1 minus 2i, take W is equal to 2 plus 3i, like that, and do all of these calculations. Do all of them. And verify that you're able to do the calculations, and that, of course, when you do the calculations, the right-hand side should be equal to the left-hand side. If it's not, there's something wrong with your complex arithmetic. This is a good test. So do all the computations and verify. It's not a proof by any stretch, of course, but just verify for those numbers, all of those properties are holding, and they do hold in general. Next up, polar form of a complex number. So we have the rectangular form of the complex number we've just been doing, and now we can have the polar form. And this corresponds very closely to what you've seen about polar coordinates. So let us just say that if we have a vector AB, we can write the, well, let's just change that. This is it to a complex number. Complex number AB, really. It's the same computation for the vector. We can write the real and imaginary components in this manner. Let me just draw you a picture of what's happening here. We've got the complex number right here. It's Z equals A plus BI. And so let me just draw these lines down like that. There's some lines. And that means that this distance right here is A, and then this distance right here is B. Okay, this is the real axis. This is the imaginary axis. Now, I'm going to draw a line here. That line is the modulus of Z, right? That is the square root of A squared plus B squared. That's the Pythagorean theorem for the 900 billionth time. Okay, now what we do is we take a look at this angle right here. We're calling it phi. A bit bigger, phi. And we're saying that A is the magnitude of Z times by the cosine of phi. Again, this is just your basic right angle triangle trig functions. So what we're then saying is, oh, and once we think of it this way, we can re-express the complex number Z as the modulus of Z multiplied by cos phi plus I sine phi. That is the polar form of the complex number. You got to be able to go back and forth between one, like the A plus BI form, and then this polar form right here. That's the polar form. The angle, this angle phi here, is called the argument of Z. Okay, and that angle is not unique. We have the usual periodicity of the sine and cosine function, which means that, you know, the sine of phi plus 2 pi is the same as the sine of phi, so, and 4 pi, and etc. So we have that if the argument falls in this range, so if that number phi right here is between minus pi and pi, we call that the principal argument. If it's outside of that range, it's still an argument, but it's not the principal argument. Let me just write this here. I could have a number here. Here's a number, Z. It has a modulus of 2, and it has a, there, it looks like it's this number right here. There it is. Okay, this thing right here, the 2 pi by 3, let me just get a different color. This guy right here, that is the principal argument. It is between pi and minus pi. So that is the principal argument. And then I could write out Z again, and this would be the same number. I could write it this way, and it would, here, I just changed this number here. This is the same exact number. There it is. And this guy here this is the argument of Z, but it's not the principal argument. Okay, we're just going to put some numbers into polar form, and we're going to put them on the graph, and then we're going to compute their product and their quotient. Okay, so we have here, we're not going to call this X, actually, we're going to change that. We're going to call this the real, and we're going to call this the imaginary axis. So let's just first get where is W. W is root 3, which is about 1.7, and root 3 plus I. So there's a 1. So W is right here. W. And then Z is 1 plus, okay, so Z is 1 plus, Z is approximately here. Okay, so we put W and Z on our graph here. We can compute the modulus of W. That's going to be the square root of root 3 squared plus the square root of 1 squared. So that is going to be 2. And the modulus of Z is also 2. That would be the square root of 1 plus 3. Okay, that's also 2. So that's telling me that this distance here, I'm just going to put it in lightly. That distance is 2, and that distance is 2. The distance from the origin is 2. Okay, now let's take a look at W. W, conjugate of W is root 3 minus I. And let me draw on here the angle phi. So maybe I'll darken this one for now. And then this is going to be phi. So I'm going to calculate phi. I'm trying to put W into its polar coordinate. So I need to calculate what that angle is. So the sine of phi is 1/2, and the cosine of phi is root 3 over 2. And then those two things together tell me that phi is pi by 6. So I can easily write W in its polar form. That's the modulus of W times the cosine of pi by 6 plus I times the sine of pi by 6. There we go. Similarly, I can do Z. You do Z. Similarly, Z is equal to 2 times the cosine of pi by 3 plus I sine pi by 3. So we've written them now in polar format. Now we can multiply. We can multiply before, but we can actually now multiply either in polar form or in rectangular form. So I'm going to do it both ways. W times Z. That would be equal to root 3 plus I times 1 plus root 3I. Okay, this is exactly what we were doing before. We introduced this polar form. So I go ahead, I distribute, I collect up the like terms, I make I squared equal to -1, and I come out here with this number, 4I. Check me on that. Do the multiplication. You know how to do this, distribute and add them all up. Okay, now I'm going to do it in polar form, W times Z. That is going to be, well, let's see. I'm not actually going to make all the calculations. I'm going to write down the answer. It's going to be like this, 4 times cosine. We're going to see this in a sec. Pi by 2 plus I sine pi by 2. Now, of course, you can do this. You can multiply this guy times this guy, and then you'll have a bunch of sines and coses all over the place, and you can use trig identities, and you can get to here. But what we're going to do right here is just notice something. This number 4 is 2 times 2, and the modulus of Z was 2, and the modulus of W was 2, and the modulus of the product is the product of the moduluses. Okay, we'll also notice that pi by 2 is equal to pi by 6 plus pi by 3. So when I multiply the two things, I'm multiplying the modulus and I'm adding the arguments. You could also take this and see, is it the same as this? You know what the cosine of pi by 2 is? You know what the sine of pi by 2 is? Right? This guy is 0 and this guy is 1. Exactly, those are exactly the same numbers. Okay, let's divide. W divided by Z. Well, we've again, that is W root 3 plus I divided by 1 plus root 3I. Okay, so you make that calculation and you get root 3 over 2 minus I over 2. And then you can calculate the modulus of that. That is 1. Okay. Go ahead and make these calculations yourself. I just don't want to spend a lot of your time watching a video, watching me make repeated calculations, but stopping the video and making calculations yourself, highly recommended. Similarly, we're going to notice that during this division, that 1, the modulus, oops, I have to cross that out. The modulus here, like that, is the quotient of the two moduli that we started with. So 1 is equal to the modulus of W divided by the modulus of Z. And also the angle phi, so figure out the angle phi from here, right? Put this into polar coordinates. You will find out the angle phi is minus pi by 6, and that is pi by 6, the modulus of W minus the modulus of Z, and that is minus pi by 3. Okay, that allows us to put those numbers on our graph. I'm going to do that right now. So what do we got? We know where the conjugate is. Let's put that guy on here. Conjugate is a reflection. So that guy is, we're at here close to, we're at 1, I guess, aren't we? We'll be at minus 1. So right here is the conjugate of W. Similar to this guy is reflected down to about 1.7, going straight through 1 there, 1.7. So we're here. That is the modulus of Z. And then we've got 4I is the product. So that is right here. So right there is W times Z. So you'll notice that it is these two lengths multiplied by one another, and then the sum of those two angles. So that's the product. And then the quotient is basically down here, right about here. That's where the quotient is. That guy right there is W over Z. So that is the length of W divided by the length of Z. This guy has that length, this length right here. And then the angle is the this angle here subtracted this angle here. Because you see these things geometrically as well. Okay, well, I was going to have a little bit more information about that. Geometric interpretation of multiplying and division of complex numbers. So we're stating this as a theorem. If we've got two complex numbers, there they are. Then when we take the product of them, we multiply together the individual modulus and we add the arguments. This is just exactly what we did. When we do a division, we divide the two moduli and we subtract the arguments. Okay, so let's just talk a little bit about of geometry. We will be asking, what is the geometric effect of multiplying a complex number by Z? Okay, I'm gonna just start here with, I'm gonna just draw it like a vector. Doesn't need to be, but I just want to be able to rotate it. There's a number 1, and then I multiply 1 by I. And so 1 times I is I, and if this is the real axis, and then this is the imaginary axis, it goes to here. So this is right here, this is I. So this multiplying by I is giving me a rotation of pi by 2 or 90 degrees. What just popped in my head there is I want you to try to start thinking this way now. Now I'm going to multiply by I again. I'll multiply this guy by I, and I'm going to get I squared. That's minus 1. So multiplying by -1, rather than thinking of it as kind of flipping, you should be thinking if I have a vector or I have a line like this and I multiply by -1, I actually rotate by 180 degrees or pi radians. The square root of -1 is I. If I multiply by I am rotating by pi by 2. With that information and generalizing, one could ask, what is the square root of I? Right now, we don't even have access of how to calculate this, but let's be thinking geometrically and saying, listen, we already knew that when we multiplied by -1, we rotated by 180 degrees. We took the square root of -1, we got I. When we multiplied by I, we rotated by 90 degrees. Maybe if we take the square root again, we will rotate by 45 degrees because each time we seem to be rotating by half. And that is indeed the case. I'm just saying if it wasn't. Okay, so really what happens here is if I multiply by the square root of I, end up here. So we can actually understand what that is. The square root of I then is 1 over root 2 plus 1 over root 2I without knowing how to calculate that algebraically. Okay, if we multiply by, if we divide by I, let's think of what it means dividing by I. Let's take something 1 over here on the axis, and we're thinking of dividing it by I. Well, I'm going to rationalize or like this, and this is going to be multiply by I here actually. So I'm going to be here I -1, and that's minus I. Okay, so what happens? I'm down here, minus I. Okay, so I'm still rotating by 90 degrees, but I am going counterclockwise. So I should have maybe emphasized when I'm multiplying by I here, I was going counterclockwise, sorry. And then here, when I'm multiplying by minus I, I'm going clockwise. Here comes two stunning formula and important formula, okay? De Moivre's formula, and that is if we have a complex number in polar form like this, z equals some number, that would be the modulus, cos theta plus I sine theta, so the argument is theta. So we have a complex number in polar form, and then z to the n, so we take the nth exponent, so we multiply z by itself n times. We can easily write this out if we have it in polar form. It looks like this. Okay, so see how easy exponentiation is in polar form. And otherwise, imagine multiplying, 1 plus 3i together, 100 times. That would be beyond painful. Okay, let's just do an example with actual numbers. It's exactly the same, but anyway. So we have a modulus there of 2, and we have an argument of pi by 3. There it is. Okay, now I'm going to ask, what is z to the 10th power? Well, I can easily just write this down. That's 2 to the 10th power times the cosine of 10 pi over 3 plus I times the sine of 10 pi over 3. Okay, meanwhile, were you to take this and attempt to multiply it by itself 10 times, that would be a huge pile of painful algebra. Let's also note that this applies to the negative numbers. So we're here. We can now find the inverse really fast here. We do this simply, that is going to be 2 to the -1 times cosine of minus pi by 3 plus I sine minus pi by 3. There we go. Okay, step 1. Step 2, Euler's formula. Okay, an amazing formula. That is that e to the I pi is equal to cos theta plus I sine theta. This is very easy to show using Taylor series. I will do that in the class. If somebody is curious about this, you think to yourself, and I think in some ways you should think to yourself, holy Hannah, where did that come from? And how would I know that to be true? It's actually an amazing looking little formula. It's tying this complex exponential to the trigonometric functions. so we can easily show this using Taylor series. So if somebody wants to ask me in the class, I will do that. I think it's pretty cool. Or try it yourself. Now that I sort of give you a major hint, you can think to yourself, oh, let me get the Taylor series for e to the x, and then substitute in e to the ix and see what happens. And do a bunch of arithmetic and play around. And you should be able to, in fact, derive this result. It's extraordinary result. So you notice that we have here cos theta plus I sine theta. And here, right over here, right here, we have cos theta. Let me just box them in the same color. There's the same, right? So then what I'm going to do is I'm going to start to write this in this like this: z equals r e to the I theta. That is a complex number in its polar form. Okay. Final point here is that let's take this amazing identity here, Euler's formula, e to the I theta is equal to cos theta plus I sine theta. This is true statement for all values of theta. I'm going to pick a specific value of theta. So it's obviously true when theta is pi. It's true for all values of theta, so it's clearly true when theta is pi. And I substitute in pi for theta, and I make the calculation, and I find out that this is telling me that e to the I pi is equal to -1. Then I rearrange slightly. Okay. We get an extraordinary statement that contains really probably the 5 most important numbers in mathematics in one statement. We have e, the base of the natural logarithm, we have pi, we have the imaginary constant, we have the multiplicative identity element 1, and we have the additive identity element 0, all in a relationship. It's one of the more extraordinary results that you get to see. That's why I like this section so much, complex numbers for the first time. Okay. My next point is going to be that given the result from the fundamental theorem of algebra, we have that numbers, we're going to see that numbers have more than one root. So for example, if you take the cube root of something, even if it's a cube root of, we're going to do 27, the cube root of 27, there is actually 3 cubed roots. If we're just talking about the real numbers, there's 1, it's 3. 3 times 3 times 3 is 27. That's what we would report. But actually, we're talking about a cube root, which is coming from a cubic polynomial, and that means there has to be 3 roots. So we're going to now identify that we can have multiple what we call nth roots. Okay, so let's just go by example here. We're going to talk about the cube roots of 27. This is our final point for this lecture. Okay, so enter this into Wolfram Alpha. Just enter it, go into it and say cube roots of 27 and see what it tells you. It's not going to just tell you 3. Okay, it's going to give you 3 of them. And this is what it's doing. We've got the number. We've got the number here. 20. We've got 27, and then here is the number 3. Okay, now so it's like, where are the other cube roots? I mean, I know that 27 to the 1/3 is equal to 3, and that my question is, are there more? If we allow complex numbers, are there more? And the answer is a resounding yes over C. So if we allow into complex numbers, yes, there's 2 more, in fact. Okay, why do I think that? It's because you can see this polynomial here, x cubed minus 27 equals 0. There, that's a cubic polynomial. It has 3 roots. That's the fundamental theorem of algebra. And those roots are when x cubed is equal to 27. So this is clearly x is a cube root of, well, I can even write that. X is a cube root of 27. We're expecting to have 3 of them. Okay, so there's 2 ways of going about this. I'm going to do the way that we can be probably unfamiliar with, that we could do given that we have the exponential form of the complex numbers. We'll just simply say, look at 27 to the 1/3. That's what we're trying to figure out. That is 27 e to the I 0 plus 2 pi k like that, all to the 1/3. Okay. This is here is giving, we have a number 27. It has length 27, and its principal argument is 0. It is on the real axis. Okay, now we're going to take the cube root, and we have that. We have here the argument can be we can add 2 pi each time without changing the number. And now we're going to be able to apply the apply what we know about using like the exponent laws. Okay, so first we're going to say what happens when k is 0. We end up with the number 3. We end up with 3. Okay, what happens when k is 1? That's just, I'm moving this thing. What happens when k is 1 here? We end up with the number 3e to the I 2 pi by 3. And what happens when k is 2? We end up with 3e to the I 4 pi by 3. And then if we keep going, we don't get anywhere. We just cycle back. Okay, so if k is 4, we're going to be back here. K is 3, we'll be back here. K is like that. So we don't get anything. So we just cycle around. We're expecting to find 3 anyhow. Now, where are these guys? Well, we've got one of them. I'm going to draw with the line so we see where they are. But one is there. Okay. And where's the other one? Well, it is 120 degrees. It's over here. This length here is still 3. That length is 3. And this is 120 degrees. And then we're over here. This is 120 degrees here and 120 degrees here. Okay, they're nicely, it's very symmetric. Okay, and then this length here is 3. So we have, these are the 3 cube roots of 27. My final point is to show you could do this without doing it this way here, although it will be slower. Okay, so let's just imagine here we take the same thing, the same polynomial. There it is. And we ask, okay, let's factor this. And that first thing we would notice is like, okay, we know 3 is a factor. 3 is a root. Is a root, right? Because 27 minus 27 is 0. 3 is a root. So that means that x minus 3 is a factor. So we know that x cubed minus 27 is equal to x minus 3 times something. Okay, this is cubic, this is linear, this must be quadratic. So we're gonna factor this out. We're gonna use our polynomial long division, which I know you love. Okay, we're gonna factor that out. We're gonna divide x minus 3 into x cubed minus 27. Okay, so I'm gonna do the first step. You know, how many times does x go into x cubed? That is x squared number of times, and then you multiply x squared, x cubed. If you can't remember how to do this or you never knew how to do it, it's not a bad time to just quickly figure it out. Okay, you subtract. This is long division. Okay, you keep going, and you'll get this. Okay? So you should make sure that you could factor a linear factor out of the cubic and get the other factor, which is a quadratic. Okay, here it is, x squared plus 3x plus 9. Okay, so I've got one factor, one linear factor there. Now I'm going to use the quadratic equation here. And I'm going to find out that x is equal to negative b plus or minus the square root of b squared minus 4ac, like that, and all divided by 2a there. Okay, so I'm using the quadratic formula to factor this guy here. And I simplify, and I find out that these are the roots right here. Okay, that allows me to write this thing fully factored, this guy here fully factored into linear factors. Looks like that, x minus, like that. There we are, fully factored. 3 roots. You could check, it's a good exercise, that these numbers, okay, so here's root number 1, x equals 3, root number 2, x equals minus 3/2 plus 3/2 I, and root number 3, x equals minus 3/2 minus 3/2 I. It is not a coincidence that these two are conjugates. That always happens. Complex numbers show up in pairs, one the conjugate of the other. Now, those are the same numbers as these three numbers. Those numbers and those numbers are the same. Two methods of finding it. Okay, those numbers are the same. What you could do is take these, use this e to the I theta is equal to cos theta plus I sine theta. Calculate those numbers and turn these numbers into these ones, or equivalently take these ones, put them in their polar form and put them back. You'll see that the answer is the same. Okay, so the nth roots of a complex number all are in a circle. I'm going to write this as a final thing I'm going to say. Nth roots of z equals r to the e to the I theta all lie on a circle. The circle has radius equal to r to the 1 over n, and they are separated by angles of 2 pi over n. There you have it. Okay, that's a crash course introduction to complex numbers. We need the arithmetic, we need the polar form, we need these two little formulas, and that's going to allow us to deal with complex eigenvalues. Okay, thanks for watching, guys, and please bring questions about this to the in-person lectures. Thanks a lot. Bye.